Welcome to topic 15.7, fission, fusion, and nuclear decay. In video 3, we're going to explore the rate at which a sample undergoes radioactive decay. And we'll use that rate to predict the number of nuclei that remain after a given time. Thanks for joining me. I'm Holly Mosley, and I teach at Liberty High School in Frisco, Texas. So let's warm up with a little bit of vocabulary. So radioactive decay is the spontaneous fission of an atomic nucleus. So we learned in the last video that fission means the splitting of the nucleus into smaller nuclei and subatomic particles. The next topic is really going to go into the specific types of decay. For right now, we're just going to focus on the rate of decay. So the time at which an individual nucleus undergoes radioactive decay cannot be determined, but decay rate can be described using probability. So we have this quantity called the half-life. It's usually denoted T with a subscript of 1/2. So the half-life of a radioactive material is the time it takes for half of the initial number of radioactive nuclei to spontaneously decay. Different unstable elements and isotopes have vastly different half-lives. Some of them are seconds, and some of them are billions of years. So let's look at an example for an element undergoing nuclear decay. So this figure shows the decay curve for a sample of radioactive nuclei of element X. And it gives the number of nuclei remaining in the sample as a function of time. So on the vertical axis, we have number of nuclei. We start at time 0 with N0 nuclei. And then on the horizontal axis, we have time, and we go from 0 to time T0. And we want to know what is the half-life of element X in terms of T0. So I'm going to look at the vertical axis for a point where I have half of what I started with, which looks to be about right there. And I see that the time that happens is T0 over 6. So that means the half-life of this element when half of the nuclei have decayed is T0 over 6. And I can go another T0 over 6, and I see that I end up with half of what I had just before that. So every time a period of time T0 over 6 elapses, then the number of radioactive nuclei has decreased by half. All right, let's talk a little bit about decay constant. So decay constant, or lambda, is related to the half-life of a radioactive material using this equation. So lambda equals the natural log of 2 over the half-life. So a material's decay constant is just another way that we can use to predict the number of nuclei that are remaining in a sample after a period of time. So this is going to come in handy when the time is not exactly equal to a half-life. Okay? Or we can use it to figure out the age of a material if the initial amount of material is known. So we know that the number of radioactive nuclei remaining is equal to the initial number N0 of radioactive nuclei times E to the negative decay constant times the elapsed time. You'll also see this written, if we just rearrange it, the natural log of the number remaining over the initial number of radioactive nuclei is equal to negative decay constant times T. So let's try this with a practice. Here we have that same scenario that we were looking at before, but a different question. We want to know how many radioactive nuclei will remain at T0 over 2. So let's start with that equation that we have, and let's figure out the decay constant. The decay constant, lambda, is natural log of 2 divided by the half-life, which we figured out previously was T0 over 6. I'm just going to rearrange that and say 6 times the natural log of 2 over T0 is my decay constant. And then I'm going to start with my equation that says the number of radioactive nuclei remaining is equal to the initial number of radioactive nuclei times E to the negative decay constant times T. I'm going to substitute in the decay constant, which was 6 natural log of 2 over T0. And then T is the time that we are looking at, which we were trying to figure out how many radioactive nuclei remain at T0/2. So I've substituted in T0/2 for time. I'm going to do a little bit of simplification, and that's N0 times e to the -3 natural log of 2, which if you calculate that out, that e to the -3 natural log of 2 is 1/8. And so we'll have 1/8 of our initial quantity at time T0/2. So what should we take away from this? The time at which an individual nucleus undergoes a radioactive decay cannot be determined. So you can't say that one's going to decay at this time or that one's going to decay at this time. We can't do that, but the decay rates can be described using probability. That half-life is the time it takes for half of the initial number of radioactive nuclei to spontaneously decay. Different elements have vastly different half-lives. Some of these are really, really fast, fractions of seconds. Some of these take billions of years. And then lastly, that decay constant can be used to predict the number of nuclei remaining after a time period or the time period that has elapsed if we know how much we have. And so we've got a couple different mathematical models that we can use to predict number of remaining nuclei or how much time has elapsed. Thanks for watching our videos over fission, fusion, and nuclear decay. See you next time.